your password. And it's like, not now, I don't. I really don't, right? I can think of a lot better stuff.
Someone actually took an AC with a plotter roll and rolled it out and then rolled it back up again.
All right, looks like we have a small group, but that's good. We can have time for questions and hopefully some meaningful content. So I'd like to thank you for being here this afternoon with us. You've got a few other places to choose, so I'm very grateful that you've chosen to join us. A few quick things. The folks at TRB have asked me to let you know that this session will run from right now until 2:30, and at that time they will be doing the closing ceremonies directly in the Kevley Auditorium. It shows in the program book that they start at 3. There's a gap in between there where there's nothing programmed, so they're going to move those forward. So right after our session, the closing session starts in the main auditorium. Let's see. Other than that, I think what we're going to do to make sure that we see all the exciting content, the run of show will be, I will introduce myself, and then I will introduce our speakers in turn. We'll probably have time for a question in between as we go through each of the speakers, and I'd ask that we hold any further questions other than maybe the one until the end of the session, just to make sure we get to see all the goodies that our presenters have for us on video. So with that, I'll start the session on geotechnical visualization. My name is Derek Dawsonbrock. I work with the Federal Highway Administration in the Resource Center and have the privilege to work on advancing and leveraging a lot of new technologies. A lot of that has been in geotechnical exploration, but now some of that's extending into the idea of data sciences, visualization, data interchange and exchange. I was trying to think of when I first, was potentially exposed to the idea of data visualization and, how meaningful that could be. And I have to think that actually goes back to maybe when I visited a planetarium or something when I was a very young child and had that totally immersive experience of being able to see everything in the night sky all at once in something that was very different than like in a book or something like that. And I think one of the interesting things about geotechnical visualization in particular is we deal in the subsurface. It is not something that you normally see, and it's up to us to examine the subsurface using different types of instrumentation or sensors or engineering geology or other backgrounds, and then to create a context to exchange with the people that are our consumers and users and the people who need to take that information and then do something with it. So I think we have a particularly interesting challenge in that realm where it isn't things that you're maybe already accustomed to seeing in space, buildings, beams, traffic, and other things. So we need to take things that you can't see and make them real for people. So I'm hopeful that we'll see some exciting things in today's presentations. So what I'd like to do is introduce our first speaker. Gabe Taylor is an assistant state engineering geologist for the Washington State Department of Transportation. He manages a small team of engineering geologists and is the geotechnical manager for a variety of transportation infrastructure projects. He specializes in slope stability, natural hazard mitigation, and emergency response to landslides and rockfall. In calmer times, Gabe juggles earthwork projects and site characterization for fish passage projects around the state. Gabe?
Hello. Derek asked me to come here to the other Washington today to provide a case example of a state DOT and how we do data visualization. And it all started with, I think, an email to my boss, the state engineering geologist, looking for some examples. And Mark knew that I had some flashy graphics and stuff and asked me to send a few along. And before I knew it, I find myself standing here in front of you. So this presentation is not necessarily, trying to show off what our capabilities are. It's really meant to just be an example of a state DOT, where we're at right now, and the challenges we face in moving forward with data visualization. So first, I need to tell you about who we are. Here's a very crude data visualization, the old org chart. I don't expect anyone to be able to read that, but you just kind of get an idea, a little snapshot. Every one of those boxes is a human being in our office. We include 12 geotechnical engineers, 8 engineering geologists, and a GIS specialist. I note that the GIS specialist is lodged in the EG section there. We'll come back to that later. We've got a whole bunch of drillers, helpers, inspectors, supervisors, admin for our in-house field exploration staff. And we've got some support staff, including some drafters. And I just learned yesterday that that term is passé. We should be talking about modelers. So there we go. I'm learning something to bring back. And we have more and more consultants in our office as time goes on. We're now close to somewhere between a quarter and a third of our staff is consultants that augment our staff. So to address data visualization, I really have to talk a little bit about where our data comes from and how we deal with it before we can visualize it, because that is really a big part of the story in talking about the challenges that we face to visualize our data. So a lot of what we do in the geotechnical office is collect the data. There's lots of different types of data. It's a big effort to collect it. And then there's this iterative loop of storing it and processing it and storing it and processing it. And mixed in with all that, there's visualization. And that is the topic of the day. But I want to talk a little bit about how we get the data in the first place. So that lump of dirt up in the upper right is actually a very complicated piece of data. It was difficult to get. We have to get a drill rig on site. We know where that drill rig is pretty closely. We have a GPS location on it. Eventually it gets surveyed. We pull that lump of dirt out of the ground. We know the depth that we pulled it out of the ground. We know the elevation of the ground surface, so we have this spatially located lump of dirt that winds up either in the sampler or on the inspector's table, and it's observed and documented carefully by the inspector, and goes into basically this little field log that's shown in the lower right there. Fairly old-fashioned, I know. There's this ongoing conversation about making this electronic, but this is the state of our practice today. So we take this field log shown on the left there, and it's very specific what goes in that log. We're very picky about what gets written down. And then the inspector has to hand enter that stuff into this Excel tool that we've developed, which gets imported into GINT. Hopefully you guys are familiar with GINT. I also probably on the outs, but we are very invested in GINT, and that's what we are still using. So our most important data visualization, it's not very flashy and potentially not even very useful to others, is the old geotechnical boring log shown there on the right. This is probably one of our most important products. It documents all of the testing and observations made in the boring. And I've learned recently that many people looking at this boring log on the right, and this slide shows sort of the process getting to the boring log. many people look at this boring log and it's not immediately evident to them what information is being conveyed. I had to sit down with a bunch of hydraulics engineers recently and teach them how to read this boring log. So I know we have work to do there as well. This lump of dirt then comes back out onto the table and is looked at by some geologists and then is sent to our lab. The lab does all kinds of things to it. They dry it, they wet it, they sieve it, they twist it, burn it, all kinds of stuff, and develop engineering properties. And those are all put into GINT. And then we have these very standard visualizations of the data that all geotechnical professionals have seen before, like this gradation plot or this Atterberg limit plot. And so right now, all this information is just being stored in GINT. And we have these standard graphical products that we pull out of that. Most of our boreholes are instrumented with some kind of instrument, typically a piezometer, which is the groundwater monitoring device shown on the left there. Data logger collects elevation of the groundwater at regular intervals. That data is then extracted from the device and occasionally brought back into our office and put into GINT. The plots on the right are slope inclinometer plots. Those are not stored in GINT. We have our own sort of in-house system for that information. More sophisticated plots are available using Python. And Python is a scripting language, a scientific scripting language that is used for mining data and presenting this information graphically. So it's very apt for our conversation today. We do have the capability of using Python. Python allows us to examine different relationships between data, subsurface data, and produce some nicer looking graphics. However, how many people in our office are comfortable developing plots like this with Python? Very few. And we're trying to get more familiar with Python. We have some training next week on Python, and I expect it to be very poorly attended. Not very many people are interested in learning how to code in Python. It's just not for everyone. I'm going, but we'll see how that goes. It's a bit of a struggle there. So pretty rudimentary plot. Many of you have seen a fence diagram. This is just shows boring logs in Cartesian space, just X, Y. The boring logs are displayed on it. We have recently added color to our fence diagrams, optional. Note, it's very rudimentary. Note, there's no ground surface. However, we produce these in GINT routinely. And how many of us are comfortable using GINT to develop something like this? It's not very many, less than half of us. We have this sort of cultural legacy where we have drafters, and we ask the drafters to do this kind of stuff. And as we put more and more data into GINT, our designers, I feel, need to have more access to it and be more comfortable making these graphics themselves. However, our drafters are a little territorial about us doing their job. And so there's a little bit of a cultural conflict there, or something that we need to manage. Much better data visualizations are available using AutoCAD and computer-aided engineering, like this one, showing basically the same information, those boring logs in the profile at the bottom, but now we actually have a couple ground surfaces. We have the plan view on the top with contour lines. It's a much better visualization. And how many of us are comfortable making this, using AutoCAD and developing these kind of things? Almost none of us. In fact, this is a plot, a graphic that I included in one of my geotechnical reports, and I had to ask a consultant to do it for me. So there's challenges there. Geophysics. We use geophysics all the time at WSDOT. We have our own in-house seismic refraction capability, seismic reflection. However, we found that it's a big lift to get out there and to do this work, and we often hire consultants to do the geophysics for us, especially because they're better equipped with other methods. So we get these beautiful visualizations of the data from our geophysical consultants. And that's actually what we get right there. It's a static image in a PDF. And there's really nothing you can do with it other than, I mean, I suppose you could design off of it. You kind of have an idea of where things are, but you can't really do anything else with this static PDF. We also don't have any kind of standard way of storing it. It's just a PDF. It goes into the project folder, right? Here's another example. Often when we get geophysical data, we'll receive these nice visualizations, but because we want to actually do more work with it, we'll request the point cloud from the consultant. And this comes in some kind of tabular format, and it's very rarely geospatially referenced. It's not like we get XYZ and lat, long, and elevation. We get some sort of station, offset, depth, and we have to figure out exactly where that survey line was done. There's a lot of post-processing required to bring that in to make a point cloud. Here's an example of this is a good example of a point cloud. I have lots of poor examples, but I didn't want to necessarily display one of those. The reason we have lots of poor examples is because we're a transportation agency, and most of our explorations are on these linear alignments. And if you have a bunch of borings in a line, you don't get a 3D model out of that. You get a profile, but it's very difficult to get a 3D model. In this particular example, we were building a new highway over a peat deposit, and we needed to characterize the depth of the peat deposit. And so we actually laid out a grid of T-probe locations where we had a geologist or a driller push a T-probe into the ground until it hit refusal and then measure the depth. And then that became a point cloud, and we made this nice visualization from that. Here's another example of a point cloud. This is displayed in ArcScene, Esri's ArcScene, and which is software that only a few of us have access to, and even fewer of us have comfort with. But this, all those red dots are points in our point cloud, and those are a combination of data extracted from borings, data from geophysical lines, and some ground surface locations selected off a LiDAR. And if I add the LiDAR to it, it looks like that. And if we spin it around a little bit and turn some things off and on, we get something that looks like this. So in this case, we have the gray ground surface from LiDAR, which is very high resolution and nice to look at. And then we have the red layer, which is the top of a glacial till unit that was of interest to the designer. And then the green is bedrock. So a lot of interpretation was required here. You know, you need to, you're looking at samples, you're looking at drilling data, you're trying to figure out exactly what the elevation of the bedrock or the till is, and it's very rarely cut and dry. So there's a lot of interpretation that goes into it, a lot of uncertainty, and when we're all done, we have this nice looking model, but what do we do with it from here? I can cut some cross sections, but if I want to convey this to a client or to someone else, they actually need ArcScene to be able to look at it, and very few people have ArcScene, and those of us who have it don't usually like it. So there's another issue there. So it's pretty useful, but I admit it's not really great to look at. And how many people in our office are comfortable using ArcScene? About 3 or 4. So another challenge there for visualizing our data. One way that we visualize or that we convey our information sometimes, is I call it a semi-solution because it's not great, is that we found that we can export our data to these 3D wireframe PDFs. And they're troublesome, a little glitchy, and you can't really use them for design, but you can convey information with them. Here's another one that we made. And at great personal risk, I'm going to try to actually show it to you right now. Let's see there it is. Okay. So this is the actual 3D PDF file. And, don't do that. Okay. Oh, which you're not seeing? Okay, yeah. So, you know what? I'm just going to move on. But I can rotate it. I can spin it around, zoom in and out of it. But first of all, when it comes up, it throws an error at you every single time. And you have to enable some kind of content, and then you have to wait, and you're not sure if it worked. And we get about a 50% success rate on actually being able to have somebody view this thing. And then once they've got it, it's kind of pretty, and you can see what we're trying to convey, but it's of no use for instance, cutting cross sections or making measurements. All right, back to my slideshow, if I can. There we go, it worked. LiDAR is a fantastic tool that all geo professionals are very happy to have these days. And those geologists who have recently retired are envious of those of us who have it now. This is a 3D model created from aerial LiDAR of an enormous landslide with a smaller landslide that's still enormous within it. So this is actually the active landslide here, and it's within a much larger feature, which is also a landslide. So this is just an example of a visualization. The aerial LiDAR, of course, is just the point cloud data, which can be hill shaded, and in this case, it's been brought into a 3D modeler and hill shaded, and we use it to delineate landslide features. So that's aerial LiDAR. We also have our own in-house capability for terrestrial LiDAR. This is a hill-shaded terrestrial LiDAR model of another landslide, actually post-mitigation, but still looks pretty ugly, but it's not burying the road anymore. So we have this capability in-house, and we often go out and scan sites and use it for collecting geometry. Once we have a 3D model, this visualization is helpful to designers for doing things like quantity calculations and other analysis. In this case, we're using it to develop cross-sections for rockfall simulation and for calculating the quantities of a cable net drape system. And in this case, we used it to figure out what the right orientation for the pre-split line on a trim blast would be to remove this unstable rock mass on the side of the highway. So these are visualizations that are probably more helpful to designers than for conveying to the public, but hey, I've managed to pull this slideshow together, so I guess it does work for that as well. As we collect more and more LiDAR over time of different sorts, this very powerful tool of change analysis is becoming more and more common. Not a very pretty graphic, and now that I've been schooled up on color theory, I've got all kinds of criticisms about it, but nevertheless, it just demonstrates the capacity of us to use LiDAR to visualize differences in elevation over time, which is extremely helpful for us who are involved with moving ground. So that was LiDAR. Another emergent technology that we're using a lot now are UAVs, or drones. We use them routinely for emergency response, for landslides and rockfall, when it's unsafe to send somebody up slope to look around, when we really need to get eyes on something that's unstable or dangerous or difficult to access. In this case, this is a landslide on the Strait of Juan de Fuca, right across from Victoria. And this UAV data, it's amazing, it's great, we use it all the time, but there are challenges associated with that too. We cannot store it on our servers. There's many gigabytes of information we get every time they fly the drone. We come back with 100 gigs of data, and our IT guys hate that. But we are able to make some nice visualizations on that. And actually, just before this presentation, I was chatting with Alex about this very thing, and he reminded me in our discussion of a really cool thing that we managed to pull off a few years ago. I'm going to try to just show it here. Oh, it's the same problem, right?
You may have to end your slideshow for a moment.
Oh, okay. I think it's worth it. Bear with me here. End slideshow. Okay. No?
We did say it sometimes takes a few moments to.
Well, there's so few of us here, I'm almost willing to just pass my laptop around, but I'm not going to. I'll go back to my slideshow. I will be very happy to put my laptop up here later and you guys can see it, but and then I'm going to resume the slideshow, hopefully. Great. Okay. How'd the presentation go, Gabe? All right. Great. Using photogrammetric techniques, the UAV is able to develop ground surfaces, just like we got all of our topo maps developed from aerial imagery back in the 30s and 40s. We can use a drone to collect aerial imagery and develop a 3D surface from that, which is extremely helpful for designers. We have not found a really great way to convey this, but it's super helpful for us. We get a point cloud, we get a surface, which we can then turn into a point cloud and bring into some software, and then we can cut cross sections on it. So for this landslide in particular, I cut a whole bunch of cross sections on it, and I'll show you one of them right here. Very crude data visualization, but there it is. It's very helpful for me. I was able to extract this cross section, which showed multiple ground surfaces, the pre-existing landslide, which you can barely see, and the existing ground surface, and then where our design graded surface would be. So that was all really very helpful way to visualize that information. Now, how many people in our office are comfortable extrapolating UAV data and developing surfaces and cross sections? None. We don't have anybody in our office who can do this, and we rely on support from other offices for this work. So one of my last topics is GIS, of course, which is probably the most common way that we visualize our spatial data, our geospatial data. There's project scale data, which we all have, and then we have these statewide geospatial data sets, and most of that is available through our Workbench, which is an agency-wide tool that everybody has access to. So that's all very helpful, and we routinely use this to do analysis and for design. And interesting little cultural divide here. We have geologists and engineers that work together side by side all the time. We have a friendly rivalry, and it turns out that all geologists know how to use GIS. We all learned how to do it in school, and some of our younger recent graduates are extremely capable with GIS. However, they do not know how to use AutoCAD. And how many engineers in our office use GIS? None of them at all. They rely on our GIS specialists to develop this kind of stuff, and it's probably underutilized on the foundation side. And like I said, the same can be said for geologists and CAD. So we have this just another challenge for us for data visualization and for building models. Yeah. We've developed web maps. We have some internal only ones that include draft data, and then we have some public facing ones. These are browser-based web maps produced in GIS. This one provides subsurface information, all of our borings and historic data. Here's an example. You zoom in on this intersection, and you'll see that there's been a lot of explorations done at this interchange. And there's a couple different colors. You see the black ones have labels on them. Those are more recent borings. They're in our GINT database. They're just like I described earlier. They're easily linked to. You can pull up the PDF of the boring log. And then there's all the little orange symbols, and those are historic explorations that may have been conducted sometime between 1930 and 1995, something in that range. And we have less certainty about the locations of those. The format that they come in varies widely. But nevertheless, we are able to display our state of understanding of this interchange through the web map. And speaking of historic documents, this is kind of what they look like when they're spread across your desk, or when you're, or maybe in your mind when you're looking at them on the screen. These are really valuable, and it's just another challenge that I want to bring up. When you're trying to characterize a site, our agency may have spent hundreds of thousands or millions of dollars exploring this site over time. There's been lab tests, geotech reports, tons of professionals have worked on this site potentially ahead of you. And where is all that information? Well, we've been working on this. We've been scanning it. We've been inventorying it and identifying it, tagging it, georeferencing it, but it still remains difficult to access. It still remains difficult to visualize. And there's always uncertainty on whether or not you've actually found it all, or if there's any more out there that's available that you haven't found yet. So just a little sidebar on that. That data is difficult to visualize. We have some other web maps. This one displays our inventory of unstable slopes statewide, and you can zoom into any one of those, and it links to our database. Same thing with our aggregate resources, big statewide data set, links to all of our aggregate resources. So I will conclude by just summarizing some of the challenges that we face with visualization of geotechnical data at WSDOT. We have statewide data sets, and we have project scale data sets. These have different formats that are stored in different ways. You can't necessarily start at statewide level and then zoom into one project and see all the information or all the work that may have been done on that project. That's a hurdle we have not yet figured out how to clear. We usually have very aggressive project schedules, and if you're handed a project and you have a short amount of time to turn it around and you're juggling 2 or 3 other projects, visualization may not be the top priority, especially because of the learning curve on new technology. A lot of the times, the designer is just going to do it the same way they did it last time. In fact, they might even open up the report that they did last time, or the folder they did last time, and change the title and start from there. So that is definitely a hurdle that we have. All the data we have, it comes in all these different formats. And I'm not just talking about the extension at the end of the file. I'm talking about the coordinate systems versus stationing and offset, elevations, and is it below ground surface or is it elevation? So we do not have a standardization there. We all speak the same language. We're multilingual when it comes to these formats, but our data is just all over the place. And then compatibility problems from one piece of software to the next. I don't know what the issue is between GIS and CAD. I mean, I do know what the issues are. I just don't know why this continues to plague us 10 years later. But these two things do not speak to each other very well, and our drafters and our GIS specialists don't get along. Well, largely because of this. They're all great people, but when you bring in a CAD layer into GIS, it comes with all the annotations and layers, and they're anyway, it's kind of a mess. So that's a problem we have as well. Our deliverables, at the end of the day, we write a report, and we don't print them out very often anymore, but they're PDFs. They have figures, they're static, they're 2D. So all this 3D work that we do is generally for the designers, and at the end of the day, it doesn't get used in the geotech report. So there was a great discussion on that yesterday and I'm very interested in trying to move that forward. And then finally, the last thing I'm just going to mention is uncertainty. There is a very famous quote that many of you have probably heard, and I believe it's associated with structural engineering, and it goes something like this. Structural engineering is the science of designing with materials we do not wholly understand, into shapes we cannot precisely analyze, so as to withstand forces we cannot really assess, in such a way that the community at large has no reason to suspect the extent of our ignorance. And that, I think it's hilarious that that's associated with structural engineering. I mean, if you think there's uncertainty in structural engineering, try geotechnical engineering. And if you really want to get freaked out, engineering geology, right? Like, we often are just making guesses at stuff. We envelope it. What's the worst it could be? What's the best it could be? So uncertainty is really an issue. And when you're trying to convey something, especially to a contractor that you have a contractual relationship with, how much information do you want to convey to them at all? Obviously, there's some kind of balance there. We haven't found it yet. Anyway, I hope this was a helpful example of where we're at WSDOT, and as an example, state DOT. And I can take a question if there is one, or I can chat more with you guys later. All right.
Any questions for Gabe? Okay, well, thank you.
Yeah.
Okay, our next speaker, standing immediately to my right, is Mark Vessely. He's got over 25 years of experience as an engineer in the transportation field, both as a state DOT employee and as a consultant, having worked on a wide range of project types and in many different locations. Mark now enjoys learning new technologies and processes and then working on the ensuing implementation challenges. So, Mark?
Thanks. How much, what do you want me to wrap? 17 and a quarter, got it. Yeah, so thanks, Derek, and thanks for everyone that's kind of made it through the day here. So I'm going to talk about a project that we worked on with the Alabama DOT and some other aspects around building a 3D site model of a landslide site, and then also kind of bringing in the fourth dimension of that and linking it to instrumentation from the field, kind of in a near real-time process. So just to kind of run down through the agenda here, I'll give a quick overview on the project site, just a quick background, won't go too much into the details. I do want to spend a few slides on the differences between how we might look at 4D data, so 3D data plus time is how I'm using that versus some of the 2D data examples, and Gabe just did a great job kind of introducing that aspect of our business. And then I just want to walk through how we're taking a pretty complex site and trying to make it as simple as possible. And then I'd like to close out just on some thoughts on why we should be doing this more and what's the value proposition, right, to get more support for this. So the site that I'm talking from today is US 231 Landslide. It was in Alabama. And there's actually a couple problems here. One is the problem of the landslide, but Gabe hit on this too. In the geosciences world, it's one of, and I think Derek said this too, it's one of, if not maybe the only area where we can't really see the problem. If I fall down the steps on the way home tonight, I go get an x-ray, they image it, I can see what everything is. None of us can image into the ground, right? There's tools we can try to, but all we're doing is trying to deduce things, or we get little sporadic pieces. So we're working in an environment that we can't see, and we're having to make decisions, which really at the end of the day is the problem. For the US 231 landslide, this is a site just south of Huntsville, Alabama. It's on a 4-lane highway, a pretty major access route in northern Alabama. It was kind of their kickoff to COVID season, shut down the road, and took about 7 months to repair. You can see some of the damage there and the Twitter feed. You know, this was big news in Alabama on on top of COVID. Road's obviously out of service there. The image on your left just shows how much the pavement's moving, and that's kind of on a daily basis. And the image on the right, I put that up there, that's what the road looked like going into this situation. It's just a nice divided highway going through the forest. What Alabama ended up doing, and I'll just let this video run, is they went to the top of the slide, they dug out as much of the material as they could. I think it worked out to like 20,000 truckloads or something like that. And then they built a bridge over the landslide. However, once they started doing the work, they realized the landslide's bigger than it is now. That whole hill slope is a landslide. There's still movement below the bridge area. So even though there's a bridge over this, they removed it. They did the best they could for the budget and the resources they had, but the landslide's still there. So it's a little bit like you know, having to, you know, go to the doctor more regularly, right? So they want to monitor this landslide through time. And so that's just a perspective of the project. Gabe helped me out with giving an introduction. When they monitor these landslides, a couple of tools we use is a tool called an inclinometer, which the best way to think about it there, that's the illustration on the left side there, is a pipe that goes into the ground, and as the land moves, it shears it, bends it, whatever, and we're able to monitor that and see where the ground's moving. Piezometer is the best way to think about that, is like a water pressure meter, and that lets us understand where the groundwater is. So those instruments were installed into that site. So now I want to transition and start talking about how we can view this 4D problem. It's a 3D site and it's changing through time, and we have the tools now to do something other than this 2D approach. I was going to say, with these images on the screen here, you could go to any state in the country and open up any landslide report, and you'd probably find graphics similar to this, and Gabe already did that for me. These are maps of a landslide. This is the site on the image on the left there. Geologist has outlined where the slide is. They put dots on the map where the borings are, where the instruments are. It's a 3D map, or it's a 3D site, right? Snapshotted into 2D. The image on the right kind of ties into the conversations in the presentation this morning, using color to try to trick ourselves into seeing 3D, right? So the red's representing steep ground, the yellows and the greens, it's less. But at the end of the day, that's still a 2D image. Another aspect of this kind of 2D world, I talked about this site and they're monitoring it with time. So the left side there shows the view from Windows Explorer for the monthly reports that they generate. And what I've done is just kind of blown up a PDF example of a 90-page monthly memo that gets sent on this project every month. So we've built the bridge, now we're generating 90 pages of information every month, and this is how it's delivered. So it's a lot of words and pictures, right? So now I'm gonna transition and bring some color in. This is a view from my office, and I don't wanna show off. I'm fortunate to work in Golden. I have a view of the foothills out my office, and you can see that table in my office. But now what I'm gonna do is I'm gonna come in and I'm using augmented reality through a HoloLens, or I have an iPad up here with the same model, and I've got it up on the screen, or up on my tabletop. It's now 3D. I've taken that 2D site, it's 3D. You can see the LiDAR, which is essentially like a really dense laser survey of the terrain, which is the gray, and the trees in the background. Now I'm gonna go ahead and start interacting with this data. So again, I'm in my office with an iPad, no different than like what I've got right up here. I've got the same model. I kind of moved it around probably, but some of you might be able to see, I have to move it, but this is in my office. So I'm walking around my table, I see a 3D model. I'm looking at the surface of this landslide. If I crouch down, or if I pick the model up, I can see all that 3D resolution. Now what I'm doing is I'm turning on different generations of LiDAR. There's a 2020 LiDAR set before the landslide, right as it happened. And then there's a 2001 landslides, or LiDAR survey set, sorry, after they built the bridge. And we can do the change detection on there. So the red and the blue are indicating where we had a lot of material taken out. That's where they've excavated it and where the bridge is. And so I'm just kind of quickly, you know, as an end user, I'm going through this process in 3D space. I'm turning on these different layers. I'm able to walk around. I'm able to look down and kind of get a perspective of that bridge in cross section. And so this is where I'm starting to interact with this now in a 3D sense, right? So now I want to kind of bring the geology back into this and the monitoring aspect and the 4D aspect. So what I've done in this view, so again, I'm still in my office, I'm looking at my tabletop, I'm wandering around, people walking by the office might look at you kind of goofy, it's like, what's this guy doing? Just, you know, because when you have a 3D model in front of you, I see it, but you don't, right? So it can look a little funny to your coworkers. But what I've done here is I've turned on everything. So I've turned on all the borings, all the inclinometers, and I'm just on top of the site, right? I'm looking just to get an understanding of the data density that I have on this site. I can see I've got piezometers, which are those groundwater points. I've got a lot of borings. I've got the highway alignment. I've got the change detection. I've basically saturated my view of the above ground of this landslide. I've given myself all the data points that I can see. Just, and I did this partly just to kind of give perspective here of what it might look like to turn that on. You can imagine that if I had to put that into one static figure, it would be a lot of information and probably hard to follow. But when it's in this 3D view, it's a little easier to move around. There and then there at the end, now I've started to transition underground, and we've got some geophysics lines, kind of similar to what Gabe showed. These are 2D lines, but we've got 4 of them, so we're able to kind of start to kind of piece together what maybe a 3D view of the geophysics. So the geophysics is, in this case, is showing the resistivity of the ground, which is a parameter that the geologists and the engineers can use to understand what's going on. Now what I'm going to do is take that same model. I'm going to go underground a little bit more. So you can see I've got that nest of stuff underground. And what I've done is I've turned on several, not all, just because it would get busy, but I've turned on the borings that are underneath. And I'm able to essentially point or touch each boring. I'm able to get my metadata, essentially my elevations, my material types, and I'm able to quickly wander around and start identifying what are the units, where are they in space relative to the bridge, and all of that. So I'm really starting to work with this in more of a true 3D sense rather than flipping pages. It's like, okay, boring number 1 and boring number 2 side by side, and where are they? It's all right there. So now I want to move into how we bring in the time component to this. So I talked about out at the site, there's instrumentation out there. There's a handful, a dozen or so of these instruments that are measuring how the ground's deforming and how the water is behaving on a daily basis. They're an automated system. It all uses, solar and cellular data. That information's aggregated on site and then it's broadcast out. It goes to the blue cloud there. That's what a cloud looks like for anybody who's curious. It goes to the cloud and it hangs out up in there and does whatever things do in the cloud. And then the HoloLens software, the augmented reality software, in this case Clerio, is able to take that translated data and it brings it into the model for the piezometers and the inclinometers. So now we're taking a daily site reading that's coming into the model, and we're able to go back and start to see this model now in 3D. So here in this example, I'm back to, you're going to see down there on the lower left, you see the little white text against my wall that says timeline scrubber. That's essentially like 3 months of time. It's moving through, and sorry, it's a little jumpy, just when you try to take it from the device into a video. But if you look up here, you see like these little red hats that are underneath, kind of just floating in space. Those are my water pressure movements, and if we were to watch them closely, or if we were to have the device on our head or using an iPad ourselves, we would see them kind of fluctuating. And And then what I'm gonna do here in a second is I'm gonna go above ground and you're gonna see graphs. So what I've done is I've selected, I wanna see the graph. Say, I could be talking to just the quotes decision maker and trying to explain to them how water moves, but they, at the end of the day, they might not really care what the pressure is or, you know, those details. But maybe Gabe and I are gonna have a conversation and he understands what I'm talking about. And so we can push the button, we can see the graph, and we'll go up top and we'll look at the graph and you can see the yellow line moving across the graph showing you where you are in time, and the little horizontal lines that you see up there are what the water pressure is doing. So that's how we're viewing this water pressure in time. Now, here's the inclinometer again. I've got my timeline scrubber in there moving, and it's really hard to see, which I'll tell you in a second is good, but you're gonna see like little thin green sticks coming out of the ground down below. Hopefully you see them. That's actually good, because these are inclinometers, they're measuring ground deformation. If they were starting to tilt over or bend, if you will, the software, the visualization is designed to start turning them red and making them into big flags. Like I said at the beginning, this is a bridge over an active landslide. They've done everything they think that they could do within the resources they could. It's good it's not moving. And green, I don't know what just happened. It just decided to shut down. Green is good. We don't want movement. But what we're able to do is we're able to take this site information on this kind of daily basis, be able to see that and quickly see that green is good, rather than that 90-page report every month. The person, whoever is interested in the data, is able to go, I'm not sure why that shut down, must have bumped something, and take a look at it. So now I just want to kind of close out here in the last few minutes. Why should we even be using this, right? And I've heard some other presentations talk about this. Some have said, hey, you know, digital twins or whatever we want to call them are at the top of the hype cycle, and others are recognizing value. The talk right before lunch was really good from New York. And really it comes down to the time value here. And if I brought in one of those 90-page memos, or I brought in the design plans or the design report for that US 231, we have a stack of paper here. Or if I brought in a HoloLens model with that same information, who would want, which one would you want, right? I think, and I don't know why it's taken me 25 years of practice to make this connection, but Gabe said we have all these boring logs. My sister's an English major. She probably thinks that they are really boring. But no, they're geologic boring logs. But in reality, in paper form, to certain users, they're probably very, very boring. So I think really when we can put 4D or 3D problems in 3 and 4D, it's just a lot more enjoyable. And this is the evidence. These are some pictures from some work BGC did on the giant mine up in Canada. Somebody was able to get pictures and the okay from the users for their likenesses to be used. But these are people who aren't in the day-to-day geosciences world, working with the geoscientists, looking at arsenic plumes underneath a mine with mine workings that even an expert in the field can't quickly deduce. And they're smiling. I would bet that if you gave somebody a 90-page memo on a monitoring report and $100, you still wouldn't get them to smile, right? These people are smiling. The gentleman on the right is a First Nations individual, so an indigenous person that's seeing this for the first time in a new way, right? And they're engaged. Just to kind of close, you know, you gotta close with the futures up bright. This is girls in STEAM, so this is high school girls in this interest in the science, and they're interacting with these models, and I think it came up in the last presentation before lunch. You know, when we look at trying to get people interested in what we do, again, I'm gonna go back to this 90-page memo. I don't wanna disparage the it, or you go to that, and I think you're gonna find a lot more people are interested in what we do when that's what they see, right? And it's also a great teaching tool. Just like you get that interaction in that last slide I showed, if you could get, if you're trying to teach and train people, and OSHA, for example, has been using this in this environment to teach excavation safety because the engagement's that much better, and it's a good thing. So with that, I just wanted to kind of put that up there, and I'm just the communicator here, really. There's a lot of help that went into this, obviously. Alabama DOT and FHWA both were sponsors on this work and helped make it happen. Dan Brown and TPL did all those design work and really made that bridge and that repair happen. And you know, at the end of the day, I'm a geotechnical engineer, and I work, in fact, one of them's right there in the front of the line, with a lot of really talented software people at BGC and Clario that make this happen. So it's truly multidisciplinary. So hopefully I got us there on time. There. Any questions? Or?
Yeah, we've got time for a question while we swap out computers.
I got a question for you. How long does it take to produce the model that you're looking at there in 3D?
So yeah, it's a question with probably with a couple answers. The Alabama model, once we had all the data, a big challenge in this, kind of like Gabe said, is just making sure that data talks to each other, and coordinate systems match, so that the LiDAR and the terrain, to build that like actual time is hours.
Got it.
And so it's the kind of thing where if you get it to
Everyone here says Caballero. I'm like,
by the end of the
but it's actually Caballero.
depending on what their workflow is, you know, it can be out in a couple days or a couple weeks.
It's just like a survey point cloud then.
Yeah.
Okay,
It's pretty, it can be drag and drop essentially.
All right, round of applause for Mark. All right, thank you. Our next speaker today, Santiago Caballero. He is currently working as a senior geotechnical engineer at AECOM. He's been working on a variety of civil infrastructure projects and geotechnical projects in Ecuador, Brazil, Honduras, Italy, as well as California, Texas, Maryland, Virginia, and the DC area. His research focuses on geotechnical visualization towards the seismic assessment of dams and levees. Santiago was a member of the NSF GEAR team after the Pawnee earthquake in Oklahoma in September of 2016.
Thank you, Derek. Good afternoon, everyone. Well, great presentations that we had today. I wish we can incorporate all of them for the industry and we can develop like a whole framework. It will be really great. But today I'm going to talk about a little bit the research we've been doing. You know, it's like pretty much like 3 schools that we're really involved in: Texas A&M, UT Arlington, and the University of Arizona. I'm going to talk about the geotechnical visualization of highly variable soils using 3D geostatistics in transportation projects. And I'm going to keep saying whatever my colleagues here said, that it's important for us to see things. And then we're not able to see the subsurface, and it's a challenge that we've been dealing over the years as a geotechnical or geoprofessionals. And I'm going to take this quote from Professor Peck, that basically your eye is the most important thing to rely about, before doing any analysis or design. So visualization in geotechnical engineering becomes like a really important topic in any critical infrastructure we can design or analyze. So visualization and geotechnical engineering is primarily graphical presentation of geotechnical data. As my colleague said, it's been a challenge over the years. Traditional methods have been used, and we're trying to incorporate new methods and new technology to improve things, to improve designs, to improve analysis and assessments. It can provide an insight into the nature of any problem, and from the concept to a risk identification of any transportation project or any infrastructure project. And then it can develop potential solutions to complex projects, such as we can do ground improvements, or we can identify areas where we can reduce uncertainties for example, for geotechnical hazards like liquefaction or lateral spreading or other geotechnical hazards too. I'm going to focus on aging and embankment roads. You know, the ASC 2021 report card released the score of this infrastructure, and then, you know, it's really, I don't like to see these scores. Is like, it's always D or D minus or towards the almost close to F. So we need a lot of work to do here, and you know, as geoprofessionals, as civil engineers, we wanted to keep improving things to you know, rehabilitate these roadways and dams and levees. And then the reason I talk about these aging embankment roads is basically most of them were being constructed using this hydraulic field method. I'm going to focus the study, my presentation on this study that we made on hydraulic field dams. You know, dams and levees mostly carry like or serve as roadways as well, and the hydraulic field process, for those of you who are not kind of familiar to this, is like kind of a really old construction method that they use, and they kind of deposit the slurry into the embankment. So basically where the coarse grain material is going to get deposited first, and the finer material is going to get you know, deposited later, or is going to flow. What is the consequence that we get when we do these methodologies? That the soil is not homogeneous anymore. And it's a problem, and it's an assumption that we have made over the years, over the decades. As a geotechnical engineer, it's like, that's the first assumption that we do. Soil is homogeneous, and then we treat it that way for any laboratory test purposes or any analysis. So that's one of the challenges we have with these earthen structures, you know, with the hydraulic field methods. And then the study I'm going to present today is a study that we did in an Eagle Mountain Lake in Fort Worth, Texas, which consists basically of a dam, which is like on the right side is like main dam, and the associated levee on the left side. Both of them serve as a roadway. You know, and basically the agency, who is the TRWD, Turin Regional Water District, these are the agencies who manage these dams, and they were concerned about the seismic effect that it could affect the north of Texas. There was a lot of induced seismicity, earthquake of magnitude of 3.5, close to 4. You know, not really high like as California earthquakes or you know, Charleston or other New Madrid areas, for example. But it was kind of larger enough to induce some movements in areas that you're not familiar to earthquakes. So we did, that was kind of the motivation to start doing this analysis. But again, the main challenge was that we were dealing with hydraulic field dams. And then this is the seismicity I was talking about a little bit. You know, a lot of magnitude larger than 3 earthquakes were happening between 2000 and 2015. And, you know, Oklahoma, Arizona, and other states were kind of climbing in earthquakes. You see here kind of a summary of earthquakes coming in the north of Texas. You know, Oklahoma has a lot of induced seismicity as well. There were a lot of agencies trying to, you know, assess the dams and levees and roadways in that area as well. The reason of induced seismicity, you know, it could be hydrofracking, it could be different things. I don't want to get into that deeper, but the seismicity is there, and then we need to kind of you know, evaluate the structures that we have near that area. So this is I'm going to talk about the main dam and the roadway that we have on top. We did the same work on the levee, and then we did a lot of in situ testing. And like Gabe was saying, you know, we do a lot of geotechnical borings. We do this CPT, which is the cone penetrometer test, and along the crest of the dam, and you see the purple points. Those are the CPTs that we did at the toe of the dam. So trying to kind of, what we're trying to do is trying to get as much data as you can to do some geostatistical analysis. Of course, we have 4 borings, the one that you see like the DBC. Those are geotechnical borings, just similar to whatever Gabe showed us, some lithologies and SPT that primarily give us some density and consistency of soil. Now, what is the CPT? And then, the testing that we mostly did on the dam consists of pushing a cone through the dam and obtain like 2 different things, basically the tip resistance and the slip friction. And then there are a lot of geotechnical correlations that we can come up with the soil type based on these 2 numbers. Now, it's really convenient because you get a really continuous data throughout the depth that allows us to obtain like soil type, like pretty much like continuously. Now, the problem that we had in these hydraulic field dams is like that it was like, as you can see these histograms here, we use univariate statistics to evaluate. It was the high variability that we have in the hydraulic field, as we expected. And then it's not, I wish like that in most of the sites that I've been working on, the soil is kind of, we can get like a layer 1, layer 2, layer 3. Most of the time that's not the case. How we can come up with a methodology to address this issue is really challenging. So what we did here, we knew based on historical records like as-built from 1932, we knew that the hydraulic field was placed in 3 different layers, and that's why we analyzed in 3 different stages, like as you can see, depth from 0 to 1.5 meters, and then from 1.5 to 6 meters, and then 6 meters to 15 meters. So you see, like in the 3 layers that were supposed to have some, some homogeneity, we don't have any, we have a lot of variability here. So what we did in this case, basically, I'm showing like a quick sketch what we have. We have CPTs on top, we have CPTs at the toe, and then we've seen like what Gabe is show us in the first presentation, what a fence diagram looks like. But what is actually happening within within the subsurface? This changes and this varies in three directions. So we use geostatistics. We consider spatial variability, stationarity, a lot of anisotropy in the data. We use the geostatistics concept that is basically based on semi-baryograms to come up with the baryograms that considers the spatial variability, the stationarity of the data, and put it into the kriging methodology to come up with a 3D visualization. And this is what we came up with. We use, of course, LiDAR, which was a really available tool at that time to come up with the surface, and then we model a 3D of the dam. On the orange portion that you see there is a sheet pile that it was installed before we did this analysis. We use, behind this, there's a lot of math involved and semi-baryograms and algorithms that we came up with to incorporate into the software. But as you can see, you can come up with a 2D section of this, and then we could identify the 4 sections of construction, how the hydraulic field was placed in 4 different stages of construction. And right at the sector 4, you see a little blue gap there, where you're supposed to have like a core dam. At the core of the dam, you have like some sandy material, coarse-grained soils. That's where we had like some seepage happening, some years ago. We were able to identify these spots through this kriging interpolation. And then what you can come up with here is like, you can do, you can filter the data. You can see here again the absence of clay material. Clay material is the finer soils that they're supposed to be in the core of the dam to kind of prevent seepage. As you see there, we have different stations, and then this helps us as a geotechnical engineers to get several cross sections along the dam to basically using different soil parameters. So on the left side, we have the undrained shear strength for fine-grained soils, and on the right side, we have the effective friction angle for coarse-grained materials. So it was a great visualization that we came up with for this dam, just using CPT data, and of course the confidence that we get in the interpolation with the geostatistical analysis is much better than just doing traditional interpolation methods. And again, we can cut sections, as many sections as you want across the 3D model, and then we can use these to do slope stability analysis, to do seepage analysis, any geotechnical assessment. We were able to identify some spots for that they were susceptible for liquefaction, some silts and sands, loose sands in the core that potentially, if you get earthquakes higher than 5, they may trigger some liquefaction. We're not expecting to have that in north of Texas, of course, but it's an advantage of this visualization. You can identify these localized areas that can be problematic in soil. And again, I've seen this from geophysical studies, and this coming out like from the CPT and from a 3D model. It really helped us to understand the subsurface. I guess we believe it's one of the tools that we should be incorporating, among LiDAR, and then, now we have the visualization in 4D, and it will be great to show it in a different way. But we have a lot of technology, and then this, framework was validated, of course. We performed some geotechnical testing at random locations. We did some lab testing at those locations, and then we compared the interpolated values with the lab testing, and they were pretty accurate to whatever we estimated from the interpolation. So basically some conclusions. Geostatistics is not like a new topic. It's a topic that has been used mostly for environmental engineering, but we've been trying to push it for geotechnical engineering. Along with the kriging interpolation and the bariogram modeling, it really produces a good visualization of the subsurface with really limited data. So that's one important thing to know. We did a lot of in situ testing, and I'm glad we had a lot of tests, a lot of data that helped for the geostatistics. But if we have limited number of data, the geostatistics is the way that the semi-bariogram models the data helps in the sense to reach that confidence in the interpolation. Especially at known locations, when you have the soil changes drastically from one location to another, then it's really a good tool to have it. Our models basically show like better interpolation using exponential semi-baryograms than other models that we have, like Gaussian model or other geostatistical. But just like, again, it's like a lot of math in there involved. But we did consider the anisotropy of the data too, which basically means that we considered the data changing in every direction in the dam. So that's something that geostatistics allows you to do in the semi-baryogram. Of course, a successful interpolation can be achieved with CPTs, again, because CPTs is a continuous data collector testing that helps us out for the statistics. For SPT is going to be really challenging because it's not continuously, unless we have like continuous sampling that that kind of helps us to get more data, but it's really challenging. It's much better when we do with CPTs. And this framework, we just recently published a paper in Journal of Geotechnical and Geoenvironmental Engineering with this framework showing that it's capable to be applied for any infrastructure, and then for any embankment or any site where you have highly variable soils. And it also is going to help you to reduce the number of explorations, which is really well, I would say a significant cost in the construction or design phase. And a lot of future research here, we've been trying to model and visualize some of the phenomena that we get in geotechnical engineering, like liquefaction or some collapse potential soils and some karst buoys, different issues that we had in the subsurface. And then there's a lot of things that we can visualize in the subsurface. And then it's ongoing research, and of course, I really would like to incorporate, what Gabe gave us in the first topic, and then what Mark was telling us to kind of see see it in the room. It will be really great to incorporate all the tools and to make it easier and more available for the industry. And again, I want to thank my advisor when I did my PhD, Professor Pupala, and my colleagues and their assistant professors right now at the University of Arizona and University in India, and of course Louis Barol and Dorota Kuterba from the Turan Water Regional District, who kind of supported research. We did a lot of work with them, help them, basically the dam and levee safe, and then they were really happy about it, and we really want to thank all of them. And then I don't know if you have any questions. Really happy to answer.
Do we have a question for Santiago while we do the swap? All right, I managed to answer everybody's question. All right, are you ready to close this out?
Yeah, I'm ready to finish this off.
All right, excellent. So I enjoyed Alex sending along his bio. He's a self-described video game developer who wandered into the wrong office and nobody asked him to leave. Okay, so Alex Ferrier is a development lead at BGC Engineering for their Cambio software platform. He has 26 years of experience in real-time 3D graphics, algorithm development, and high-performance computing. His experience in video game development includes roles as the technical director of products including the Need for Speed and NBA Live. Since 2019, he's been developing geotechnical engineering software, including BGC's GPU-based M3C2 point cloud change detection algorithm and the Cambio 3D visualization tool. Thanks for being with us.
Thank you for having me, everybody. The future is coming. And I think we've seen so many presentations over the last 2 days that show that a step change in the level of visualization we can achieve is coming, and that people will interact and engage with these presentations like never before. Elite high-end video game teams are now targeting 100 million vertices per frame. I have screenshots here from the next Assassin's Creed, Forza Horizon 5, and that level of data can be used to generate compelling stakeholder visualizations. And everybody agrees with that, so I don't need to stand here and tell everybody that. So let's talk about what else we can use that power for. We can use that power to connect visualization to raw engineering data instead of worrying about making separate decimated models for visualization or generating custom content for visualization. And by doing that, we can enable engineers to communicate and make better decisions faster. So I'm going to run through a number of pieces of work that we are working on to help push that work forward. I'm going to start with the need for engineering cross-sections and why they are so important in communicating both topography, the state of the surface that you can see, and subsurface, which you can't see. 3D visualization is great. It's fantastic for stakeholder engagement because everybody can immediately look at a 3D rendered picture and understand what is being shown to them. Here we have a section of the I-70, major east-west corridor across the US through Glenwood Canyon. And you can see immediately that we have a deep valley. We have cliffs. But unfortunately, 3D visualization, when you want to use it for engineering and numerical analysis, is actually surprisingly useless. What is the elevation at the base of those cliffs? What is the angle of that slope? I have absolutely no idea by looking at that. A cross-section is the tool that engineers use to communicate topography and subsurface, and every single engineer has drawn one. You start with some contour lines on a map, you place your ruler across them, you project them down, and you draw effectively a graph saying, I draw this line in a plan view, and this is what elevation data looks like across it. And every engineer understands this. Unfortunately, that mental transformation from line on a map to cross-section is very difficult for a large section of stakeholders to do. And for this reason, it's very difficult to use a cross-section to communicate in a public engagement. Wouldn't it be great if we could communicate by seamlessly transitioning from and to cross-sections? Here we have a mapping application, it's our Cambio application, which supports 2D and 3D maps. And here we are viewing a section of a national park. We can view this as a hillshade, zoom in and out. We see that we have a road through here and some rock alignments. Now let's cut a north to south aligned cross-section through that data and transition seamlessly into an engineering view, which is one-to-one scale, numerically annotated, and allows us to communicate engineering data. Similarly, what is the grade of this road? Well, we can just cut a cross-section parallel to the road's center line, zoom in, and we can see immediately in a graph form what the grade of that road is. We can zoom out, let's cut across the entire valley. What does a cross-section of the whole valley look like? Notice how as we seamlessly transition from 3D view to cross-section, it's very easy for anyone to understand the relationship between the cross-section and the plan view or the 3D view because we never cut, we do so continuously. LiDAR is absolutely critical to all modern site investigation of geotechnical structures. It has completely transformed the industry, and the raw form of LiDAR is a point cloud. Unfortunately, one of the first things that we do, because GIS applications are so commonplace, is reduce that to a 2.5D gridded structure. And we do that at some resolution, but unfortunately 2.5D grids, obviously, as their name implies, are not actually a 3D representation. If you have a complex rock slope, if you have overhangs, none of those can actually be represented in a grid, and a lot of geotechnical investigation involves extremely steep or complex rock structures. So we want to push forward the state of technology and democratize access to point clouds, because in doing so, we can give people access to better data and help them make better decisions. Also, the presentations before me introduced LiDAR change detection. Here we have a landslide and also some cross sections that we have drawn, showing how we can compute change detection, shown in blue for negative change, red for positive change. And it's important to note that usually when computing change detection on a point cloud, we want to do it as a fully three-dimensional calculation, not just an elevation change calculation. We do that, and we do it on GPUs so that we can run that analysis at regional scales. I am a software developer, not an engineer, so I want to digress slightly into the computing science behind our change detection. There are two types of processor in modern computers: the CPU, or central processing unit, which has been the main unit that we've done computing on since the 1960s, and a new one called the GPU, which is the graphics programming unit, but was originally called the graphics programming unit because it was used for 3D graphics. Nowadays, all modern, complex scientific software runs on GPUs, and the G for graphics is a total misnomer. When people talk about running on AI processors, I promise you that they are running on GPUs. The most studied problem in the history of computing science, which is, given a user scrolling on their phone through cat videos, which advertisement do you show them to make the most money, is a problem that you solve using GPUs. And the power of GPUs is how we interrogate, analyze, and visualize large geotechnical data sets. Okay, let's look at an example. Here we're going to show the Glenwood Canyon I-70 debris flow, which was a result of some wildfires in 2020, followed by an above-average monsoon season. Here is some results of our corridor scale change analysis, and we can see a pile of red there, which is the results of a large debris flow. We actually already have systems for panning through maps and analyzing large amounts of this change detection data, which still requires engineering expertise, understanding of the geology of the area, understanding of the behavior of slopes. But we can use visualization to make understanding what is happening with change easier. So here we have a 30-kilometer-ish section of Glenwood Canyon. All of this was recorded live. And we're flying through, looking at those areas of positive and negative change where we can see that there has been change between the 2016 LiDAR and the 2021 LiDAR. I'm not going to make you sit whilst I fly through 30 kilometers of terrain, so let's just fly straight through it. But it's very easy to understand the relationships of change in slope to the structure of the slope itself. And in fact, as we fly past here, we will see exactly the same area of change detection that we were previously showing. If you look up the slope, you can see the blue negative change of that debris channel as it was cut through. A second debris flow further down here, and again we can come through further and we will come to the Blue Gulch debris flow, which actually completely took out the I-70 for a while. And you can see this massive channel of negative change as huge volumes of material flowed downhill during this rainfall event. Visualization like that is great. What's more powerful is visualization like that combined with analytics. And I slightly misframed things with the camera there. The reason Blue Gulch flowed so massively is that cliff band, 100-meter cliff band that you can see up there. And you can quickly see visually the difference between above and below the cliff band. But numerically, we can quickly analyze that and see that there was 100,000 cubic meters of change. How deep is that channel? It's difficult to hike up that slope. Well, let's cut to an engineering cross-section showing the before and after terrain. You can see that's a 15-meter deep debris flow channel cut through in this event. Again, we can cut a cross-section parallel and show both topographies, so 2016 and 2021. And you can see the scale of the change that happened here. So by giving people better access to LiDAR data, we can help them make better decisions more quickly. I want to talk a little bit about visualization and the importance of human scale navigation. Every engineer, when they go to the field, understands best practices for taking photos as part of a record. One of them is always include an object for scale. So when using our applications, we always keep you as a human avatar in view. This immediately allows you to understand how big is this rock face that you can see here. Camera systems are critical. Interacting with an environment is much more visceral and powerful than simply visualizing 3D of an environment. In fact, I would define them as completely different things. Video games work because they immerse you in an environment rather than simply allowing you to view an environment. In a traditional 3D viewer, tumbling multiple kilometers of terrain, if you just rotate it with your mouse, is a very unintuitive operation because your brain hasn't evolved to understand what rotating multiple kilometers of terrain around looks like, because it's not a thing we actually do. So we can leverage knowledge of camera systems to allow us to build systems that give us better understanding through visuals. Here we are in Yellowstone National Park, Northeast Entrance Road. There were a lot of constraints on this work to look at alignments of rock faces. One of them is that we weren't allowed to use drones at all. The park board does not want people flying drones in parks, because once somebody flies drones in a park, everybody thinks it's okay to fly drones in a park. So you can see data collection here being performed using a tethered balloon and a camera. So all of the photogrammetry that you're about to see was actually collected from a balloon. Photogrammetry allowed us to collect this data more safely and more quickly than traditional climbing across a rock face. We're going to show this data directly as a point cloud. We did not generate a 3D mesh from it. This is a 140 million point cloud rendered in real time. And again, we can apply the principles that we talked about previously. We have an avatar. We can run around this environment. We can navigate seamlessly around this environment with cameras, with weight. And again, this allows us to understand the detail of the structure that we are analyzing and get to making engineering decisions more quickly. So why didn't we use a mesh there? There's a bunch of reasons. We're very short on time. I'm not going to go into all of them. Meshes are actually unbeatable as a representation of arbitrary geometry. But a mesh is a derivative product of a point cloud, and it takes you time to get. If you fly a drone, you can generate a point cloud in 10 minutes. Then it takes 2.5 hours probably, to generate a point cloud. So by making data able to get to the 3D view more quickly, we can enable more rapid analysis. And also, we don't have all of the artifacts like you can see on the mesh on the left, where a lot of the structure of the mesh that you perceive if you look at the geometry is actually how the algorithm has cut it up to texture it, rather than anything to do with the surface. Point cloud rendering can be extended. Here is a very quick fly-through done in about 7 minutes of an extended area, including a second rock face, which is higher than the first one that we showed. What we're going to show here is actually the 2020 public LiDAR, just directly rendered as a point cloud. It's not perfect because it's about 40 centimeter spacing, but it does accurately represent what was captured. And that's interesting because when we see holes in the rock faces, which you can see on the right, that, as an engineer, is actually useful information. Rather than meshing and making up data, we at least acknowledge that our remote understanding has not captured that surface. We can then inject a photogrammetry point cloud that we captured alongside that LiDAR point cloud, embedding both together and allowing us to view our dense data in sight with a much larger region, which we can just use LiDAR to capture. And point cloud rendering is great because you can basically use point size as a way to implement variable opacity. That lets you blend layers of point cloud on and off and switch seamlessly between them. So, the future's almost here. The massive increases in compute power that we have happening are going to make some really exciting things happen in visualization. I don't need to tell anyone this because there have been so many presentations that have already demonstrated this. My plea would be that we can do even more than that by using this power to not just make prettier visualizations, but to tie it to denser, raw engineering data. We can enable more rapid iteration of visualization of that data, and that, in turn, can help us make quicker and better decisions. Thank you.
We have time for maybe one question if anybody has anything that they'd like to ask Alex as we close the session today.
Thanks, everybody.
Okay. For those of you that may have come in after I made the very early introductory remarks, the closing session, although it's printed as starting at 3 o'clock, they're looking to move it forward, so it'll be starting in the main Kevley Auditorium now. So we should all head that way. But I would like to thank you for attending this afternoon's session. I personally think we had the best visuals and the visualization of the conference. So another round of applause to our speakers, and we'll hope that they publish their work. So thank you for joining us this afternoon.